World Guidance, World Modeling and Condition Space for Action Generation by researchers from ByteDance Seed and the University of Hong Kong. Here's the core problem for anyone building vision language action or VLA models right now. There is a massive computational trade-off. If you try to predict raw future video to guide a robot's physical actions, it is computationally redundant and far too heavy for real-time inference. But on the flip side, if you use latent action models to aggressively compress those future states, you lose the fine-grained precision required for complex millimeter-level manipulation. The authors of this paper propose a solution called WOG, or World Guidance. Instead of predicting raw video or relying on coarse latents, WOG introduces a two-stage curriculum to build a highly compact condition space. Stage 1 compresses future visual observations into dense condition tokens that explicitly guide action generation. Stage 2 trains the VLA to predict those exact conditions internally, using only current observations. The result is a highly efficient predictive space that drastically improves fine-grained manipulation, like folding a deformable towel while maintaining incredible out-of-distribution generalization, completely outperforming baselines like Pi0, OpenVLA, and video prediction policies.
That sums up the breakthrough perfectly. It is a fundamental shift in how we handle predictive modeling for physical agents.
Okay, let's unpack this. For those of you actively building in the embodied AI space, getting a VLA to accurately model the future is, it's basically the holy grail right now. You want the robot to anticipate the physics of a manipulation task before it fires a single actuator. But the compute tax required to actually do that has been an absolute nightmare.
It really is. It's the primary bottleneck holding back scalable real-world deployment. If we survey the landscape right now, the research community is largely split between two deeply flawed approaches. The first is world action models.
Right.
And these architectures force the system to predict explicit future modalities. So you're asking the network to generate future RGB image frames or depth maps or optical flow, or, slightly better, you're trying to predict generic semantic features from a foundation vision model.
Which sounds great in an academic paper until you actually look at the tensor sizes and the inference latency. Why force the model to calculate the exact pixel values of a shadow moving across a desk when all you want to do is pick up a wrench?
Exactly. That is the exact problem. It's massive redundancy. These semantic spaces are completely task agnostic. They force the model to compute visual overhead, like how a background reflection changes or the trajectory of a person walking behind the robot.
Yeah, stuff that doesn't matter.
Right. It provides zero actionable signal for the actual manipulation task.
Yeah.
It's an enormous waste of FLOPs that just completely bogs down the control loop.
It's like calculating the trajectory of every leaf blowing in the wind just so you can safely cross the street. It makes no sense. So to avoid that massive compute tax, the other half of the research community pivots to latent action models, or LAMs. But that introduces a totally different headache, doesn't it?
It does. LAMs attempt to solve the compute crisis through aggressive compression via visual reconstruction. The goal is to find embodiment-agnostic, high-level motion patterns. But, as the authors of the WOG paper astutely point out, the way this compression actually behaves in practice is very similar to principal component analysis.
Wait, so it's essentially just extracting the maximum variance signals from the visual data?
Exactly that. It captures the loudest, coarsest motion trends.
Okay.
If you're routing a mobile base across a warehouse floor, capturing that macro-level variance is fine. But when you need fine-grained millimeter-level control, say, for inserting a peg into a hole or grasping a very thin cable, that PCA-like compression has completely smoothed over the critical high-frequency spatial details.
It's the classic dimensionality reduction trap. You probably run into it in your own ML workflows all the time. You want a lightweight model, so you aggressively compress the data. But then you realize you just deleted the critical nuance required for actual precision.
Yeah, you lose the signal with the noise.
Exactly. It's like giving someone driving directions by only telling them to drive north for 10 miles, which is great for high-level routing, but entirely useless when they need the micro adjustments to steer around a pothole.
That's a great analogy. Finding the middle ground between those two extremes is the central tension of this entire paper. The pivotal challenge is defining a predictive space that is computationally tractable for a VLA to forecast in real time, but still expressive enough to guide highly precise action generation.
So that brings us to the actual architecture of world guidance. How do we build this Goldilocks predictive space? Let's dive into this two-stage training curriculum.
The brilliance of WAG lies in how it constructs what they call the condition space. Stage 1 is entirely about building this space using perfect future knowledge. During this first training phase, the VLA receives the current observation encoded by a standard vision language model backbone. But crucially, it also gets to cheat. It is fed future observations.
Let's pause on that. They are feeding it future frames, but how many? What's the action horizon we're looking at here?
They sample 4 future frames to cover a 16-step action horizon.
4 frames. Got it.
But they don't just dump raw frames into the model. They pass these future frames through 2 distinct frozen foundation vision models. They use DynoV2 to extract deep patch-level spatial and semantic features, and they pair that with a WAN VAE to capture the temporal dynamics.
Okay, for the engineers listening, why that specific pairing? DynoV2 makes total sense for spatial understanding, but why throw a variational autoencoder into the mix?
What's fascinating here is the complementary nature of those 2 models. DynoV2 is exceptional at understanding what an object is and its geometric properties, but it lacks an understanding of motion over time.
Right, static.
Exactly. The WAN VAE, specifically trained on video data, captures how pixels flow and deform across those 4 future frames. Combining them gives you a rich representation of both the what and the how of the future state.
But wait, we just established that raw semantic features are too heavy. We have DynoV2 features and VAE features for multiple future frames. If we just concatenate all that, aren't we right back to the computational nightmare we were trying to avoid with world action models?
We would be, which is why they project those combined features into a unified embedding space and introduce a trainable Q-former-based future encoder.
Okay. Let's get into the mechanics of that Q-former. For those who haven't implemented one recently, how does it actually compress that massive feature space without catastrophic information loss?
The Q-former utilizes just 16 learnable query tokens. Think of these queries as highly targeted searchlights. They use cross-attention to sweep through the dense DynoV2 and VA features, extracting only the dynamic information that is strictly relevant to the action being performed. And they managed to compress this down into a condition space with a dimensionality of just 32.
Just 32 dimensions.
Just 32.
That is incredibly dense. So in stage 1, the model is taking this tiny 32-dimensional cheat code of the future, feeding it into the action head alongside the current observation, and basically learning how to generate perfect robotic actions.
Precisely. It learns optimal manipulation based on perfect, albeit highly compressed, future knowledge. But as you know, at inference time, the robot is flying blind. It doesn't have access to future frames.
Right, unless someone invented a time-traveling camera for robotic arms that I haven't heard about. The robot only has the live feed of what's happening right now. So how do they bridge that gap in stage 2?
Stage 2 is where the model internalizes the future. That Q-former-based future encoder we just trained in stage 1, they freeze it completely. It becomes a stable mathematical target. Now, the VLA must learn to infer that exact 32-dimensional condition space using only the current observation.
Freezing the encoder sounds incredibly risky, though. If the real-world camera feed at inference differs drastically from the stage 1 training data, doesn't that frozen mathematical target become a rigid liability?
It could, and that's why they use a dual-loss approach in stage 2. They introduce a new set of learnable query embeddings that perform cross-attention with the last hidden states of the VLM backbone. They apply a cosine similarity loss to force these new predictive representations to align with the target conditions from the frozen encoder.
Man, I can already hear the groans from anyone who has tried tuning loss functions and representation learning. You're balancing cosine similarity for the future condition while simultaneously trying to minimize the standard action prediction loss. Don't those two objectives just fight each other?
They absolutely can fight each other, which is why the stage 1 condition space needs to be so pure. Because the 32-dimensional space was explicitly bottlenecked by the Q-former to only contain action-relevant dynamics, the cosine similarity loss isn't forcing the model to hallucinate background noise.
Oh, I see.
Right. It's only forcing it to predict the essential physics of the next 16 steps. The result is that the VLM extracts necessary predictive logic from the current frame and bakes it directly into its internal weights.
Here's where it gets really interesting. Let's look at the actual simulation benchmarks. Because architecture diagrams are great, but the proof is always in the success rate. The researchers tested this extensively in the simpler simulation environment, mapping to both Google Robot and WidowX configurations.
And the comparative data is stark. Across all visual matching tasks in the simpler environment, WOG achieves a 69.4% overall average success rate.
Let's put that in context for everyone. I was looking at the OpenVLA baseline, and it's hovering down around 33.8%. That is practically a coin toss for a robotic action.
It really is.
Hmm.
And even highly optimized newer models like Pi Zero Fast cap out at 60.5%. GR00T N1 is at 48.4%.
Yeah.
When you jump from those baselines to nearly 70% average success, you're looking at a fundamental paradigm shift in reliability. It's not just an incremental fine-tuning bump.
Looking at the breakdown, there are specific tasks where WOG just completely separates from the pack. The pick, coke, and move near tasks are prime examples. For pick, coke, WOG is hitting an 89% success rate.
Tasks like picking up a specific object or moving a manipulator near a target rely heavily on understanding object affordances and executing a precise trajectory. That 32-dimensional condition space provides the action head with the exact, subtle physical cues required to navigate the end effector efficiently without overshooting.
But I want to pivot to a really fascinating limitation the authors transparently report, because it's important not to treat this as a magic bullet for every conceivable physical interaction. They note that WOG does not yield a distinct advantage in spatially sensitive placement tasks, like the stack task. Why is a model that is so good at physics fail at stacking blocks?
This raises an important question about the limits of condition modeling. WOG acts as a powerful amplifier. It magnificently amplifies a foundation model's inherent strengths by stripping out perceptual noise and focusing purely on dynamics. However, stacking isn't just about dynamics. It heavily relies on static 3D spatial geometry. WOG cannot magically inject new spatial semantic reasoning into the system.
So if the base vision model doesn't natively understand 3D spatial geometry well enough to perfectly align a block vertically, predicting the future condition won't fix that base deficiency.
Exactly. The condition space is built on top of the Dino V2 and VLM features. If those backbones struggle with millimeter-precise vertical spatial alignment, the compressed condition space will inherit that exact same blind spot. The model can only guide actions based on what the vision backbone is actually capable of perceiving.
Let's move this out of the simpler simulation environment and into the real world. The lab setup is a UR5 robotic arm utilizing a Robotic 2 F85 gripper with an Intel RealSense D435 camera mounted top-down to provide global observations.
They designed 3 distinct real-world tasks to stress test the boundaries of this conditioned space. First, they have close the microwave, which is a classic test of articulated dynamics.
Right, understanding how a rigid door swings on a fixed hinge.
Exactly. Second is a standard pick and place involving rigid objects like cups and plates. And third, the ultimate nightmare for fine-grained robotic control. Fold the towel.
Anyone who has worked with deformable manipulation knows why folding a towel is so brutal. You are dealing with practically infinite degrees of freedom when you manipulate fabric.
It's chaotic.
It really is. The robot has to grasp one bottom corner of an isosceles triangle folded towel and perfectly align it with the opposite corner. The success threshold is less than 5 centimeters of distance between those corners. You have to plan a highly precise trajectory, but crucially, you have to nail the release timing so the fabric settles correctly.
It is highly complex. But under in-distribution testing, where the lab environment perfectly matches the training demonstrations, WOG hits a 100% success rate on the microwave, 60% on pick and place, and 60% on folding the towel.
A 100% success rate on the microwave is almost unheard of in physical robotics. Is that a testament to the condition space, or is close the microwave just a highly constrained task with low variance?
It's a bit of both. The trajectory of a hinged door is mathematically predictable once grasped. But traditional models often fail because they get confused by the visual changes of the door swinging, reflections on the glass, or changes in shadow. WOG's 100% success rate proves that its condition space perfectly isolates that underlying hinge dynamic, completely ignoring the visual noise.
Then what about the towel task?
For context on the towel task, the Video Prediction Policy, or VPP model, only managed a 45% success rate. So 60% is a significant leap.
But let's talk about what happens when the real world stops looking like the training lab. The classic out-of-distribution, or OOD, problem that plagues every engineer trying to deploy physical AI. They tested some truly devious variations here.
They really did. They threw 3 distinct OOD scenarios at the UR5 arm. First, a severe background change where they swapped the standard grid tablecloth for a solid pink one. Second, a lighting change, projecting numerically controlled, harsh shadows directly onto the workspace. And third, novel objects, asking the robot to manipulate unseen blue towels or cups with completely different colors, shapes, and handles.
I've seen state-of-the-art models completely collapse when you just change the lighting in the room. Are you saying WOGS just ignores the shadow completely?
It dominates the O tests. Look at the background change during the towel folding task. WOG only drops from a 60% success rate to 50%. Let's compare that to Univi, which drops from 20% all the way down to a 10% success rate under that exact same pink tablecloth. Or look at the harsh lighting change on the towel task. WOG drops to 35%, while Univi plummets to 10%.
This is where the architecture choices really validate themselves. Why doesn't the pink tablecloth or the harsh shadow completely break the model's brain?
Think about what a standard video prediction model does in an OD scenario. If it's trying to generate raw future pixels to guide its actions, it has to waste massive compute trying to render the pink pattern on the tablecloth, or hallucinate exactly how the new shadow will stretch across the desk as the robotic arm moves.
It's forcing the model to solve a real-time rendering problem instead of a physics problem.
And that's where WOG's 32-dimensional condition space acts as a strict bottleneck. It actively discards redundant perceptual noise. It only distills the manipulation-relevant dynamics like the geometric deformation of the cloth itself. By completely bypassing the need to generate high-dimensional visual predictions, WOG becomes remarkably robust to visual shifts that don't actually alter the physics of the task.
Which brings us to scaling. As you all know, these VLAs are incredibly data-hungry. How does WARG scale when we move past a few hundred curated lab demonstrations? The authors utilized a massive data set of human manipulation videos to push this further.
The scale of the data pipeline here is staggering. They ingested a data set collected via PTO4 Ultra Enterprise VR headsets. We're looking at 1,920 total hours of egocentric human video.
Nearly 2,000 hours, but only a fraction of that was annotated, right?
Only a 220-hour subset was actually annotated with specific actions. In that subset, the human wrist joint pose relative to the VR headset was mapped to the robot's end effector, and the human hand opening was mapped to the gripper state. The vast majority of the dataset, however, is completely unannotated human activity.
And they took this a step further with the Universal Manipulation Interface, or your UMI, data experiment. The UMI rig is basically a handheld gripper with cameras attached to it, right?
Yes, and if we connect this to the bigger picture, UMI is designed as a universal interface for capturing in-the-wild robot data. The authors wanted to test if WARG's condition space could handle training on UMI data, which consists of completely egocentric human observations with unseen embodiments, rather than the fixed, top-down camera setup of their lab.
So you're asking the model to learn physics from a human hand holding a UMI rig, and then execute those physics on a rigid UR5 arm with a top-down view. Does the condition space actually translate across that massive embodiment gap?
It translates beautifully. Incorporating the UMI data resulted in a 33% relative improvement in the towel folding task and a 42% relative improvement in pick and place. Because WARG abstracts the scene into that dense mathematical condition space, it can effectively extract the necessary physics from egocentric human observations, completely ignore the fact that the embodiment is a human hand rather than a UR5 gripper, and map that underlying dynamic logic directly to the target robotic workspace.
So what does this all mean? Let's summarize the primary takeaway for those of you looking to integrate these concepts into your own architectures. By moving away from predicting every single pixel of the future, which wastes compute and falls apart under out-of-distribution noise, and by avoiding over-compressed latent actions that destroy fine-grained control, WAG finds an optimal, highly efficient middle ground. By predicting a compressed, 32-dimensional action-relevant condition space, we get VLA models that are computationally tractable, highly robust to visual noise, and precise enough to fold a deformable towel under harsh lighting.
And I want to leave you with a thought to mull over as you return to your own research. If WAG's condition space is mathematically stable enough to extract raw manipulation logic from unannotated egocentric human video, and then cleanly project that logic onto a completely different UR5 robot arm, could this kind of abstract condition space eventually act as a universal translator between biological movement and machine kinematics? As the industry scales up to full humanoids with dozens of degrees of freedom and entirely different actuator dynamics than standard industrial arms, could predicting these generalized physical conditions entirely replace the need for rigid joint angle telemetry in our training pipelines? It strongly suggests that the future of robotics might not be about mimicking joint angles at all, but rather translating the pure intent of physics.
Keep questioning, keep building, and we'll catch you on the next deep dive into the literature on AI paper podcasts.